This video is the first in a three-part series on the spherical capacitor. And in this video, the goal is to simply compute the electric field in the space between the two conductive shells of the capacitor. So we see our spherical capacitor on the left, and it's made of two concentric conducting shells, the inner one with a radius of A and a charge of plus Q, and the outer one with a radius of B and charge negative Q. And the spherical symmetry of this distribution tells us that the electric field should point radially outward. Now, to find the electric field magnitude between the two shells, we're going to invoke Gauss's law. And Gauss's law says the electric flux through a closed surface, that's the integral on the left of E dotted into dA, is equal to the enclosed charge divided by epsilon 0. And I'll post a link at the top to the derivation of Gauss's law. So we're going to choose a Gaussian surface that shares the symmetry of the charge distribution. So we're using a spherical shell with radius r, where r is between A and B. Note that in the region inside the inner shell, in other words when r is less than A, we're not going to have any charge enclosed by a Gaussian surface there, and this means the electric field is going to come out to 0 in there. And it's also true outside the outer shell, so if r is greater than B, our enclosed charge would still be 0 because we have a positive Q and negative Q adding up to a total charge of 0. So the electric field is 0 outside the outer shell. This means the only non-trivial region to analyze is the region between the two plates. So when r is between A and B, we want to find that electric field between the two shells. So we get into applying Gauss's law, and we want to start with this flux integral on the left. So we have the integral of E dotted into dA over the entire surface. Now remember, the area increment dA carries the direction of a normal vector to the surface, in other words, a radial vector in this case, and that means E is always parallel to dA. This means the dot product is trivial, and our dot product of E dotted into dA turns into a simple product of E times dA, where E is the electric field magnitude. Next, we use the fact that with the entire surface of our Gaussian surface equidistant from the center of this configuration, E must have a constant magnitude over the surface by symmetry. As a constant, that E can be factored out of the integral. So I end up with E times the integral of dA. Well, the integral of dA is just the surface area of this Gaussian surface. And the surface area of a sphere is 4 pi r squared. So our flux integral is done. Now this is going to be equal to the enclosed charge, which we called plus Q, divided by epsilon 0. Solving for E, we find that the electric field magnitude between these plates is Q over 4 pi epsilon 0 r squared. And we notice this turns out to be the same as the electric field of a point charge located at the center of the configuration. But keep in mind the difference here is that E is equal to 0 inside the inner shell, so when r is less than A, and outside the outer shell, so when r is greater than B. In the next video, we use this electric field to compute the potential difference between the shells, after which we can quickly find the capacitance of the spherical capacitor. That video is linked at the upper left of the end screen, and I'll see you there.